Hey everyone, I guess I've been teaching this lecture for a few years now, twice a year, and I'll tell you a bit about why I'm doing this and what's been particularly exciting about fusion energy, what it even is, and some of the metrics that you should think about if you think about fusion anytime. Um, so I guess just over 2 years ago, something pretty spectacular happened not very far from here, over the Bay Bridge at Lawrence Livermore National Lab. The National Ignition Facility, which is one of, I don't know the exact number, but probably like a dozen fusion machines that are currently in operation at national labs around the world, achieved ignition, which is to say that in the experiment that they conducted, they produced more energy out of the experiment than was put in. This was a monumental milestone, one never achieved before, and has kind of spurred a lot of both work, discussion, and excitement about fusion thereafter. So I put this graph in. It's a classic scientific graph that is not super pretty. But the things that I want you to focus on this, the black lines represent that National Ignition Facility, that fusion machine that's presented there. And on the y-axis, you have something called Q, which I'll go into a little bit later. But basically, with those black lines increasing over time on the x-axis, that represents multiple experiments that have been done at that national lab. Since that December 2022 achievement, there have basically only been, so what's interesting about these national labs is that for the most part, national labs tend to have their utility mainly has to do with defense, or at least in the case of the Lawrence Livermore National Lab and the National Ignition Facility, that's its use case. But for the purpose of researching the ability to produce power out of fusing atoms together, they only had the ability to run something like 8 shots in the space of the last 2.5 years, and and in those experiments, the most recent one that actually hasn't even been announced, so y'all are privy to information that that isn't widely known. They were able to achieve something like close to 3 times more energy out of the system than was first put into the system. So, in case you don't quite realize how amazing this is, it's basically harnessing the sun, which is what we're going to get into. It's something that has never been achieved before in the world, and it's basically something that will determine how our energy systems are likely to change very significantly over the next few years, and represents a whole new industry of opportunities for you all to eventually work in. So why am I talking about fusion? My background, probably like some of you, is in chemical engineering. I basically set out to work on the intersection of energy and climate when I first decided to study chemical engineering in undergrad. I went on to do a PhD to figure out what are some of the key technologies required to resolve climate change. And I didn't study fusion, but what I did do before going into venture capital, which is where I am now at a firm called Lowercarbon Capital, that has a couple $2 billion to deploy into decarbonization technologies. The thing that I did just before that was work on energy policy with utilities across the U.S. And state agencies that wanted to figure out, some of them had decarbonization goals, some of them didn't, and just knew that basically the amount of electricity demand was going to grow significantly. They wanted to figure out what those resources were. And why I've been so attracted to working on fusion and investing in companies developing fusion technologies, because those options were actually quite few and far between, like solar, wind, energy storage. Many of the things that you've learned so far have grown very significantly in terms of deployment. That's critical, and that is going to continue to grow. But one of the things that became very obvious was that for electricity to be reliable and affordable for the majority of the country, and the rest of the world, you would need things called baseload energy. So meaning things that could be turned on and off whenever you wanted to, or could be on all the time. And actually the options for those are pretty limited. So there's natural gas, there's coal, there's nuclear fission, which you might have learned about. And to make that clean, you can tack on carbon capture and storage, something I studied. But fusion energy represents basically the holy grail of being able to offer clean baseload energy. And given the other options there were only a couple of them, and honestly, they just had a bunch of challenges, whether it was environmental concerns or community acceptance around radioactive waste, etc. Just left me pretty dissatisfied, and looking to fusion and seeing the progress that has happened is really quite exciting. So again, that's why I do this work, and that's why I'm here presenting more about fusion to you today. So what is fusion? Harnessing the sun, what does that mean? So the sun shines bright because basically atoms are fusing together all the time. I don't know how many gazillions, but a lot. And it was in the early 20th century that researchers were like, oh, okay, so we're starting to understand how that works. Let's see if we can replicate that on land. Wouldn't that be cool? The research and work and funding around it only really got started in the 60s, and then had kind of waves of funding, and where there was more or less, basically kind of following whenever you had an energy crisis, like, oh, we're running out of oil because we're going to war with the Middle East, and then, oh, we discover we have oil here in the US, and so less funding goes towards fusion. That's a little bit of what has determined that. So anyway, back to it. What is fusion? Fusion is the act of fusing two light atoms together and producing a heavier one, and a huge burst of energy. It is the most dense source of energy on Earth. It is the opposite of nuclear fission, beware. In fact, in some circles, people don't even like to call fusion nuclear because it just makes it sound like fission, and the two could not be more different. Nuclear fission, as you've learned, is the conversion of heavier atoms into lighter ones, and a lot of energy. The difference between the two, so that, but plus the fact that in order to fuse two atoms together, you do actually need to put energy in to get that fusing to happen. And what that means is you can't actually have any thermal runaway reactions. And another reason that's important, or just to think about, is so how do you actually fuse two atoms together? You get enough power, energy, so that they overcome the forces that are otherwise keeping an atom together, and the forces that would otherwise repel equal charges, that Coulomb barrier. And so you need to get to a point where those things, that Coulomb barrier can be overcome, and you're fusing those atoms. Fun fact that we don't necessarily always think about, but the majority of the energy resources that we take advantage of today are some derivative of the sun. Not just solar PV, but also fossil fuels. Ultimately, that was only in place because of photosynthesis, which is the sun, etc. Wind power is a differential, and it ultimately is generated by a differential in temperature that creates those wind streams. So, but fusion is really the crux of like the most dense thing that you could do. And just to put that into perspective a little bit, I like this schematic, and if you'll note for later, these are different units that are representing kind of the energy output per mass of fuel. But importantly, fusion is 100 times more dense than fission fuel, about 6 million times more dense than natural gas, 10 million times more dense than coal. And when we talk about fusion fuel, most often we're talking about isotopes of hydrogen. In fact, we're always talking about isotopes of hydrogen, but most often we're talking about two specific ones, deuterium and tritium. An isotope, reminder, it's the same number of protons, different number of neutrons. But ultimately, you're working with some of the lightest atoms, and I'll get to why that is shortly. So, and deuterium and tritium, tritium we'll get to is actually a pretty scarce, but you can access that by accessing very small amounts of lithium, of which there is actually quite an abundant amount. And the deuterium or other isotopes of hydrogen you'll find in water. And to put that into perspective, 1 barrel of water and just a fraction, like less than 1% of the amount of lithium that you'd have in an EV, translates to powering 50,000 homes for a year and about 750 barrels of oil, whichever metric you prefer. Fusion, the ability to harness fusion power creates no long-lived radioactive waste. Like I said, you actually need power to make the reaction happen, so there is no thermal runaway, obviously no CO2 emissions, which is something we care a lot about, and like I said, inherently safe. The other thing that you produce in this deuterium tritium, in fusing deuterium and tritium, is that burst of energy and then a high-powered neutron, which we'll get to, that has some implications. And specifically, so I mentioned those isotopes, but some folks are working on, and like there's a lot of research around other fusion reactions. I'm hesitant to say reaction. Because then that makes it sound like a chemical reaction. It isn't a chemical reaction. It's a thermonuclear one. But anyway, we're going to use that word for now. But so there are other. So again, there are other atoms that you can work with to generate fusion energy. This graph on the top right, the main thing to remember there is that the y-axis is the probability of the fusion rate, and the x-axis is, on the bottom one is kinetic energy, on the top one is temperature. The reason that those are both on the x-axis is basically there's a direct relationship between temperature and kinetic energy. There's just a constant that makes that conversion. So often, instead of talking about tens, hundreds of millions of degrees Celsius, which is the temperature in the sun and what you would need to harness fusion, we talk about keVs, which effectively is kinetic energy. But the point is that what this graph shows is that under that blue line is that deuterium tritium reaction that I referred to. That's the one that is kind of most researched, most well understood. And the reason for that is that the area under that curve is the largest and is the one that starts at the lowest temperature. Why that matters is that basically you have, imagine you just have a larger operating field to be able to achieve high fusion rates. But there are advantages to other fuels, to other fusion fuels that people are exploring, in particular ones that don't produce that very high-powered neutron, because the high-powered neutron can break through basically some of the highest grade steel, and so there are some things that need to be done from a material science standpoint to make sure that isn't just like destroying everything in its pathway. The main metric that is referenced when talking about fusion is something called the triple product, otherwise known as the Lawson criteria. That's the product of plasma density, temperature, and confinement time. And as a rule of thumb, just think of 10 to the power of 21. That's kind of the minimum triple product required to achieve break even, which means producing more energy out of the system than is going into the system. And this very busy graph basically plots that triple product on the y-axis against temperature on the x-axis, and all of these dots reflect the kind of dozens of fusion machines that have been built over time. And in the top right, some of the most recent results at the National Ignition Facility that have gone beyond that 10 to the power of 21 number. And the reason that number is important is it's a proxy for what we refer to as that Q value, but ultimately the amount of energy coming out of the system that is put into it in the first place. The ways in which you are talking about Q basically have to do with what boundaries you are putting around your system. So the result that happened at the National Ignition Facility achieved break even a Q value much greater than 1 when putting that boundary around the fusion fuel pellet. So that's what's called scientific break even, when the boundary is around the fuel plasma system only. The next things that you want to achieve are engineering break-even, when you're putting that boundary around the heat and confinement and energy required to confine the plasma, and then finally a kind of full facility, or otherwise called wall plug break-even, that includes all the ancillary systems that are needed for a fusion power plant to basically operate. And this graph is different from the previous one because here on the x-axis you have time, and on the y-axis still that triple product. But what I would note here, and the y-axis is on a logarithmic scale, is that in the last 70 years of research into fusion, that triple product has increased by 7 orders of magnitude, or about 40% increase per year. That's the equivalent rate of Moore's law, if you've heard of it, the kind of what effectively semiconductor cost decline, or chips known more colloquially, follow. So that's huge, because mainly Moore's law is often referenced as something that's like, oh, this is very, very fast. This is growing exponentially. Well, so is this. And so that's a lot of like what happens at the atomic level and what has been happening in these different experiments. How do you actually put this into a power plant? And I'm going to reference a few different fusion machines, but first, just to think of the broader system, what you have in the middle there is the plasma, and DT refers to that, and the neutron refers to that fusion fuel, and then the neutron produced. And what you have around it is often a lithium blanket. That lithium blanket basically harnesses the heat that is produced from that huge burst of energy, and a working fluid is taking that heat and effectively running a steam turbine that generates electricity. And then from there on, that's the same process that you will have learned for many other systems. As you may already be thinking, wild, an insanely complex system, is actually just generating heat to run a steam turbine, like most basic thing that was invented a very, very long time ago. Why? Good question. Some people are working on this. Not enough people are working on this. There's definitely an opportunity for more research in that area for direct energy conversion. That goes into more electrical engineering that I'm less familiar with, but it is possible, and more research needs to go into it. One of the things that I flagged earlier is that tritium, which is one of those fusion fuels, is actually quite scarce. That said, it's and it's expensive because it is scarce. But it's actually very easy to make in a fusion system, because by basically hitting that lithium blanket with those high-powered neutrons that are produced in that fusion reaction, I can't find a better word for it, produces tritium. And so that tritium is then recycled in the system, but also more of it is generated within that fusion machine. And there are a couple of specific types of fusion machines that have been most researched that you might have heard of before. On the one hand, you have magnetic confinement fusion, which is basically the ability to confine that plasma. And I didn't define plasma, but maybe some of you know this already. It's kind of the fourth state, if you will, ionized gas, where electrons are free flowing, and you're basically targeting the nucleus and getting that fusion rate to happen. But so what magnetic confinement fusion is the ability to confine plasma thanks to a very strong magnetic field, and that strong magnetic field can be created by superconducting magnets, low temperature, high temperature. Those are some of the options. And how does that translate back to that fusion triple product? Since that's the main thing we're looking for in these fusion machines, is it requires relatively low plasma density, low temperature, and long confinement times. You have some example names of fusion machines built there. What I would note is that Spark is one of the tokamak fusion machines that is being built by a private fusion company as opposed to a national lab. Inertial confinement fusion, that's the other category, one other category of fusion, but the other category that has been most researched. The fusion fuel is compressed and heated heated to plasma thanks to very quick bursts of energy imploding on a fuel-filled target. And that burst of energy can be generated by high-powered lasers or projectiles or things. And it requires, contrary to magnetic confinement fusion, it requires relatively high plasma density, high temperature plasma, but very short confinement times. They're typically talked about pulses, very high bursts of energy. That schematic represents the National Ignition Facility over in Livermore that I mentioned, and those blue beams here are the 192 lasers that were required to make that experiment happen. So just a quick read on some of what has happened in fusion. There's a long and very annoying saying that suggests that fusion is always 30 years away. There have indeed been, there's about 60 plus years of research that has gone into fusion. The amount of funding that has gone towards fusion at the kind of public level is only $35 billion, which to put that into perspective, or in my terms, in the US alone, there's about $200 billion that goes into venture funding every single year. If you think about what went into the NASA COTS program, that's hundreds of billions of dollars, and this is effectively just a fraction of that. That has happened all over the world, but right now, something that is catching a lot of people in my world's attention is the fact that China is putting a lot of money towards fusion, and just in the last couple of years, they've earmarked multiple billions of dollars to build several fusion machines. And meanwhile, it's kind of the U.S. and much of North America and Europe that has pioneered a lot of the research, the majority of the research around fusion to date. The other interesting thing is that private funding to fusion has also been growing. That has mostly grown in the last, say, 4 or 5 years. In the time that I have been working on fusion and investing in fusion companies, that we went from something like 2 billion to 8 billion. And again, that's just in the last 4 years, basically. And this is kind of a smattering of where that has happened. Again, some of those largest funding rounds have happened in the US. CFS refers to a company called Commonwealth Fusion Systems. That is the best funded fusion company in the world. You're like, okay, cool, private funding. Why does that matter? And what are some of these tailwinds that are getting this private funding to grow? In just the last few years, the amount of private companies building fusion technology or working on fusion has gone from something like sub 20 pre-2020 to over 70 globally, and that funding has increased materially. And that's why I as a venture capitalist am here talking about fusion and effectively investing in fusion companies. Okay, so you have some background on what fusion is. Well, I'm sure you'll have lots of questions that hopefully I can answer. But the context, again, for which I'm here and why I'm talking to you about fusion is in 2021, Lowercarbon Capital decided to raise a fusion fund, and from that we built a fusion portfolio. And so, what I hope you are starting to glean from what I've presented so far is that there are actually many different ways that you could build a fusion machine. There are many different types of fusion machines. They actually come, and what I'll show you now is that they actually come in lots of different sizes. They rely on different supply chains and even different talent pools. And that's why ultimately in the public realm, there has been so much funding to different fusion machines. That said, even that has been concentrated to just a few. But with tailwinds like new materials coming up, computing being much more readily available to a wider set of the population, AI, of course, enabling modeling and simulation to be a lot faster and more accessible. that has created new opportunities in fusion technology that were never really there before. And those things have both fueled the private industry, but the private industry has also been fueled by the fact that fusion technology has progressed very fast. Like I said, it actually tracks an exponential curve, very similarly to Moore's law. And what that means is folks working on fusion were tired of staying with public with kind of the public funding or national lab type pace. The technology had gotten to a point where they could take that out of the national labs. There are real concrete proof points to reflect that a lot of the physics risk that was once unknown or risk is no longer there, and things like various energy crises that we've kind of been going through in the last few years, whether it's the war in Ukraine that drove up energy prices very significantly across Europe, but more generally the ability to basically maximize our own kind of technological superiority, but also energy security, has fueled the starting of many private companies, great talent going out of the national labs and starting companies, and then also private capital going into it. And so I'm going to somewhat quickly run through what our portfolio has now been constructed to look like. And as I previewed, it's basically taking advantage of it, but recognizing that fusion systems, fusion machines come in many different designs, whether it's the tokamak, the stellarator, inertial confinement, something called magnetized linear inertial fusion, the Z-pinch. There are a lot of different reasons why you'd want to investigate these systems. This is a representation of the tokamak. The thing to note here is mainly that it requires multiple types of magnetic fields and coils around it. That means that there's a certain level of complexity and cost involved in generating those magnetic fields. And Commonwealth Fusion Systems is probably the leading company building a tokamak. And what they've taken advantage of is innovation around high temperature superconducting magnets that make those systems way more compact, tokamaks way more compact than were ever envisioned before, and actually start putting them on the map for being a type of machine and power plant that could be cost effective. And just to give you some sense of that, on the top is the tokamak that is currently being built at something called ITER in France. It's it's a kind of international collaboration in the public realm, and that representation below is what ARC CFS's tokamak power plant or commercial demonstrator rather will look like in comparison, and that's because of that innovation in materials around high temperature superconducting magnets. A fun schematic of something called the stellarator. It's another form of magnetic confinement fusion. The main thing to remember, which is very visual, is that the magnetic field that is required around the stellarator basically is very complex, and so is represented by these very twisty coils. That has historically been considered pretty untenable to build. The advantage of it over the tokamak is that the plasma is meant to be a lot more stable, and in theory, you would need to put less energy into the system to get an equivalent amount of energy out. But again, those coils look insane to make. Where there has been opportunity to innovate, and where companies are innovating, I flagged two companies here in our portfolio, Renaissance Fusion and Thea Energy, is in basically taking what otherwise looks like a hardware problem and turning it into a software problem, which is to say that this is something that Thea Energy is doing, where they're piecing together smaller magnets and controlling the magnetic field created so that it is replicating that twisty magnet feel without being twisty magnets. Renaissance Fusion is also innovating in that realm, but in their case, basically instead of building the twisty magnets, they are presenting a kind of a sheet of high temperature superconducting magnets and etching the magnetic field, if you will, so that again, it doesn't have to be so physically complex. Inertial confinement, that's again what happened at the National Lab, the National Ignition Facility. It's the ability to that's basically using very high powered lasers to compress, to heat up and compress a fusion fuel pellet to create more energy out. You saw in an earlier schematic that the that NIF for short has 192 laser beams to do that. Where there's been innovation is around one, cheaper lasers. So what's being used there is solid state lasers, or glass lasers rather. Exemer Energy, a company out in Colorado, is innovating by basically using something called Exemer gas lasers that are a lot lower cost. Those costs have been driven down by the semiconductor industry where that's used. And they're also able to provide a lot more. Those lasers can provide much more energy, a higher energy output from the laser itself, which means that they'd only need 8 lasers instead of 192, 8 or 16, one or the other, but a fraction basically. And here, this is another example of an innovation around basically eliminating the need for magnets and lasers, but instead taking advantage of advances in something called capacitors, and some demonstrations that have happened in other national labs, like Sandia National Lab, on something called the Z machine. Pacific Fusion is a company being built very close by over in Fremont. They have basically $1 billion earmarked for them to build a facility that should demonstrate the ability to produce about as much energy that's going into the facility than was put into the facility. And when thinking about innovating in fusion, there's certainly a big capital need, and the fact that they have unlocked that and are taking advantage of a field of fusion and physics that have been researched and are known, and adding kind of new technology to that is very emblematic of what the private sector is doing around fusion. And then something called the Z Pinch. Zap Energy is a company out in Seattle that is basically building a 50 megawatt system that fits in the front of this lecture theater. No magnets, no lasers, but instead it's a high burst of energy that is created through a very large electric current, and basically understanding how that will confine to plasma is kind of key to that. These are other ones that are innovating in the non-thermonuclear realm. Muon catalyzed fusion is basically the ability to use something called muons, which are subatomic particles, to bring that fusion fuel together and force that fusion to happen instead of having to replicate the 100 millions of degrees. That would be very cool. And they're over in Boston. And Avalanche is another one, leveraging what's called inertial electrostatic confinement. Again, I guess what's very exciting about this to me is that what these companies get to do is apply a different kind of skill set, but also a different way of working. A lot of the kind of, maybe you've heard of the kind of SpaceX, like build and iterate type model, and that's a lot of what these companies are looking to apply, so as to really accelerate the access to fusion power. In conclusion, so I went through a lot, but I guess what I would love for the takeaway to be is that there's a lot of the fundamental plasma physics that has been demonstrated at this point. There's talent going into this. There's capital going into this that are funding the path to commercialization. There's a DOE milestone-based program that is replicating what happened in the kind of race to space, that sets out the milestones required to build a commercial fusion power plant in the 2030s. The other thing that is very exciting is the fact that I'm sure you read about AI or use AI every day, but and you're maybe have also seen the headlines about how AI is fueling the next is fueling basically our need for a lot of load growth, a lot of energy generation growth, and they have become one of the first customers of fusion power and are effectively committing to buy electricity generated by fusion power plants in the 2030s. You have companies that are starting to site those commercial fusion power plants. The regulatory landscape has basically just determined the distinction between fusion and fission, which is really important, getting these things built fast. And there's still a lot of growth and kind of there are a lot of engineering challenges, a lot of opportunities for growth, whether it's on the material science side or sourcing some of the inputs that I mentioned. And then I think there's an exciting opportunity for basically new industries to grow as a result of fusion in the kind of manufacturing of lasers, like I said, new materials, capacitors, and magnets. This is a replica of one of the graphs I showed earlier, basically that triple product on the y-axis, time on the x-axis, and some of how we built our fusion portfolio at Lowercarbon basically maps out to the different lines that represent different types of fusion machines that have had research over time.
With lithium becoming very popular for EVs, is there a reason why we use lithium and not other metals for fusion systems? Are there any other sources that would work?
Yeah, that's a great question. So, I mean, one of the things to note is that the amount of lithium needed is very, very small. And when you're building that fusion system, you're looking to produce tritium from that lithium, and then you're looking to recycle as much of it as possible. So I think I mentioned it's like um, for that equivalent of 50,000 homes for a year, it's like less than 1% of the lithium that you'd need in an EV. I don't know. I don't think that, like, from an isotopic standpoint, you would be able to use other atoms, but I don't have the periodic table totally. Or like, yeah, they haven't talked about any other ones, or others haven't been researched to my knowledge. But it's a very small amount, and actually, lithium is pretty abundant on Earth. The challenge has mainly been that a lot of the places where we're producing it from produce it very unsustainably. But the other thing that I'm excited about is you have new technologies that are making it much easier to extract lithium.
How did you develop your expertise around energy technologies like fusion that you need for your work as an advisor for Lower Carbon Capital?
Yeah, thanks for asking that, and thanks for suggesting that I have all this expertise. um, well, I was hired at Lowercarbon initially because of my background in chemical engineering and combining that with the work that I had done in energy policy and kind of energy startups. I apply what is mainly in engineering and kind of like understanding at a high level the laws of physics or thermodynamics and ensuring that the things that we're things that we are seeing and obviously potentially backing have clear founding in research or like an ability for that to be plausible, right? There's a lot of leveraging expertise outside, engaging with academics, spending time at the national labs to understand like what are those next frontiers, what are the challenges that you foresee, what are the opportunities that you see. That has helped basically create a lot of this strategy around like, yeah, what fusion machines are actually could actually be viable in some future. And yeah, I'm excited about what's next. So thanks all.